Hello, scholars. Can you hear me? Hello.
Yes.
Yeah, I was having a technical problem. So I was having, that's why I haven't logged in since. But I'm glad now it's resolved. So we can begin. Um, Today we round up the data description. Okay. So we'll start with empirical rule. So our main topic of discussion today, empirical rule and Chebyshev. Now, make sure you can see the screen first. So empirical rule, according to empirical rule, for data sets that have having a distribution that is approximately, I'll make it bigger, a little bit bigger. This is too small right here. Make it 16. That's better. So for data set that have a distribution that is approximately bell-shaped, which is called, we can also call it normal or symmetric. That said, having that, the following properties hold. About 68% of all values fall within one standard deviation of the mean. About 95% of all data values fall within two standard deviations of the mean. And about 99.7% of all of them fall within three standard deviations of the mean. I'm going to explain that in a minute with this chart here. See? You can see here, this is the mean, population mean. This one represents one standard on the right side. This represents one standard deviation of the mean, two standard deviation of the mean, three standard deviation of the mean. Then on the left side, the same thing. One standard deviation, two standard deviation, and three standard deviation. So it says here that approximately 68% of data values fall within one standard deviation of the mean, which means that from here, this is 34 plus 34 will give you 68%. So it means that from here, okay, from this point, one standard deviation to this point will give you 68%. That's why that's what that statement means. And they also say that approximately 95% of all data values fall within two standard deviations of the mean. Okay. Now it means that if you add from this place, add from two standard deviation to the other, this section 2. So you add 13.5 plus 14 plus 34 plus 13.5 will give you 98%. Sorry, 95%. You can verify that with your calculator. Then it also say that approximately 99.7% fall within three standard deviation of the mean. Okay, what does that mean? It means that for three standard deviations of the mean, we're finding from here all the way to this. So if you add this, 2.35% plus 13.5% plus 34% plus 34% plus 13.5% plus 2.35%. You add all of them, you're going to get 99.7%. Again, you can verify this with your calculator. Okay? So from there, we're going to look at some of the more concepts under this. We consider data entries that lies within two standard deviation of the mean to be, that lie more than two standard deviation of the mean to be unusual. So from here, any data value that lies more on this section, which is below two standard deviation of the mean, or above it, which is two standard deviation, is considered to be unusual. Let me use a chart to show you that. Let me start with the usual values. From here to this is considered usual. For example, normal body temperature of a human being, normal birth weight of a new baby, normal blood pressure, normal blood sugar level. So anything that falls within two standard deviation is considered to be normal, usual range. Now, on the business side, if in Maryland, most teachers, their annual salary is ranging from $50,000 a year to $80,000 a year, which is usual. Normal. But if you see a teacher in Maryland that is making $120,000 a year, that is unusual. Or if you see a full-time teacher in Maryland making $25,000 a year, that's unusual as well. So that's something called normal range, which is considered the usual range. Now, the unusual, anything above normal, which is mean minus 3 standard deviation, or mean plus 3 standard deviation of the mean, is considered to be unusual, which means that this section from here to this is unusual. You can see right here, unusual. And also from this spot here, from this on the right side is also considered to be unusual. As a matter of fact, one that is bigger than 3 standard deviation is considered to be very unusual. So empirical rule, we use empirical rule for any data set that is symmetric. So what am I trying to say here? I'm trying to say that empirical rule applies to symmetric or bell-shaped distribution. So, which means that if the distribution is not symmetric or bell-shaped, we cannot use empirical rule on it. And the formula we normally use is this. We call it the general, the equation for expressing the range of values within the Kerr standard deviation around the mean. We call it mean plus or minus Kerr times standard deviation. So on the left side, you have mean minus Kerr times standard deviation. As you can see here, everything on the left side is mean minus the Kerr times standard deviation. On the right side, we have mean plus Kerr times standard deviation, which you can see from here. On the right side, mean plus Kerr times standard deviation. So now we'll come back to a empirical rule and when we start solving problem. Let me use this opportunity to introduce Chebyshev theorem. Chebyshev theorem, according to the available published evidence, says that the position, let me make it bigger. Okay, let me make it a little bit bigger. That'll be good. Okay, make all of them bigger. Okay, make it 16. So what Chebyshev is saying that the position of any data set lies within Kerr standard deviation of the mean is at least, or let me put it in a different way. The position of any data set lying within Kerr standard deviation of the mean, where Kerr is greater than 1, is at least 1 minus 1 over Kerr squared times 100%, where Kerr represents the number of standard deviation from the mean. So according to Chebyshev, at least 75% of data values fall within 2 standard deviation of the mean. At least 89% of them fall within 3 standard deviations of the mean. And at least 94% of the data values must fall within 4 standard deviations of the mean. So unlike the empirical rule, we use Chebyshev theorem for all distribution, whether it is symmetric or not. But usually when this distribution is symmetric, it's better to use, in fact, it is recommended to use empirical rule. It is only when it is no longer symmetric that you can use Chebyshev theorem. And in general, we use the following equation for expressing the range of values within Kerr standard deviation around the mean, just like we have in the empirical rule. Mean minus Kerr standard deviation on the left side and mean plus Kerr standard deviation for the left side. Now, if you want to estimate Kerr, there's some question that will ask you that in Chebyshev that reflect Chebyshev theorem, or some question they will ask, or you'll be asked that will require you to use Chebyshev theorem, but will first of all require you to get the value for Kerr. that case, this is the formula for getting K. Either you use the upper end or you use the lower end. And for both cases, it's still the for upper end, you're gonna be upper end minus mean divided by the standard deviation. And if you are using the lower end, you can say lower minus mean divided by the standard deviation. Yeah. Now, when we start using those formulas, you see that they're not really that bad. So let's try one. It says here that past results from the National Health Survey suggest that the pulse rate of women have a mean of 76 and the standard deviation of 12.5. Assume that the distribution is symmetric. Now I say that assume that it is symmetric. That will automatically tell you that you're going to be using Chebyshev here. Sorry, using an empirical rule here. It says find the minimum and the maximum usual rate for women. Then determine whether a pulse rate of 110 will be considered unusual. So to answer part A, we know that from the chart that I showed you that the usual rate is within the range of mean 2 standard deviation on the left side and 2 standard on the right side. So that means we're going to use this formula: mean minus 2 standard deviation for the lower end, lower rate, and mean plus 2 standard deviation for the upper rate. So we're going to have it here, and I have it written here for you. First of all, let's say that the mean for women is 76. I have it here. Mean equals 76. And the standard deviation is 12.5. See, 12.5. So now let's get the upper end and lower rate. Minimum is mean minus 2 times standard deviation, which means 76 minus 2 times the standard deviation of 12.5. Okay. So let me write this down and we can get it from the calculator. 76 minus 2 times 12.5. Okay. So 76 minus 2 times 12.5. So let's see. We have on the calculator, we have it in this form. So you have 76 minus 2 times 12.5 give me 51. So 51 beats per minute on lower end. 51 beats per minute. Now for the upper end, a maximum rate, we use something, except that this time around we use a plus sign. Okay. Excuse me, plus sign. So that means we go to the calculator and add, may change it to plus sign. Okay. Plus sign. That was 101. 101. 101 beat per minute. Beats per minute. So that means that the minimum and the maximum rate for women is 51 beats. From 51 to 101 beats per minute. So we answer part A. Now part B says a pulse rate of, determine whether a pulse rate of 110 will be considered unusual. Okay, of course it will be considered unusual because remember the rate is from 51 to 101. So 110 is more than that range. So it is unusual because it falls outside the usual range. Any question on this? Yeah, no question. Excellent. Now let's try another example because I might ask you the question in different form. Let's try this one. It says here, the mean speed of a sample of vehicles. The mean speed of a sample of vehicles are measured, where is it again? Oh, right here, sorry. The mean speed of a sample of vehicles along a stretch of highway is 7 miles per hour with a standard deviation of 4 miles per hour. Assume that the data set has a bear-shaped distribution. So you say assume that it has a bear-shaped distribution. That will tell you automatically that we are going to be using empirical rule. You say estimate the percent of vehicles whose speed are between 63 miles per hour and 71 miles per hour. And assume that data set is bear-shaped. Okay. Now, B said, suppose that the number of I make it let me make this other than 16. Okay. Now it says suppose that the number of vehicles in the sample is 75. Estimate the number of vehicles whose speed are between 63 miles per hour and 71 miles per hour. And in a sample of 25 vehicles, that part C, how many vehicles would we expect to have speed exceeding 71 miles per hour? So the first thing is to write out the mean and the standard deviation. Okay? And then you make your chart in this form. These numbers are set on stone. So you can't change them because they're the empirical rule. Remember, the empirical rule says that I think I moved too far away. It says that 68% of all data values falls within one standard deviation of the mean. So if you divide this 68% by 2, okay, you get 34, 34. So all these numbers are shaped on a stone. So you just memorize this chart because that's what you're going to be using for solving empirical rule problems. So for this particular one, our mean is 67 and the standard deviation is 4. So we need to get this value from the chart. Mean is 67. Mean is at the center. Okay. 67. And the standard deviation is 4. So to get other numbers for this place, you add the standard deviation on the right side. So 67 plus 4, 67 plus 4, since the standard deviation is 4, right? Yeah. So 67 plus 4, look at the calculator. 67 plus 4 gives you 71. So you go and put 71 right there. Here, the 71. Then plus 4. You keep adding 4 until you get all the answers for these formulas here. So plus 4. So 71 plus 4. Okay. You get 75. Okay. 75. You can put 75 for this one. 75. And 75 plus 4 will give you 79. Okay. Now you repeat the same thing for the left side, but on the left side you subtract. So you gotta the mean is 67 and standard deviation is 4. 67 minus 4. So 67 minus 4, you check it on the calculator. 67 minus 4. 67 minus 4 is 63. Okay. You can put 63 right there on the left side. So you go on the left side, you can put 63 right there. Okay. So you put 63 here. 63. Then to get this one, do the same thing, subtract 4 plus this one. It can give you 59, I believe. You can double check this with the calculator. 59. And 59 minus 3, so minus 4, will give you 55. You can verify this. Okay. 55. Okay. So I'm gonna make the adjustment. Okay. So everything's done. So with this, now you can be able to answer those questions. It says, first one says, estimate the percent of vehicles whose speed are between 63 miles per hour and 71 miles per hour. So 63 to 71, 63, let me write it down. On 63 to 71 miles per hour. Okay? So look at the chart. And this is your 63 right here. 63 to 71 miles. So the percent will be right here in front of you, 34 plus 34. So the percent of vehicles whose speed are between 63 and 71 miles per hour is equal to 34, because this is it right here. 34 for that range. 34% plus 34%, which is 68%. You can verify this. So we answer part A. So the percent, it goes from here to that. Now for part B, part B says, suppose that the number of vehicles in the sample is 75. Estimate the number of vehicles whose speed are between 63 miles per hour and 71 miles per hour. So we have the percentage here already written as 68. So that the number of vehicles whose speed, I'm going to make this to be 16. So that means that the number of vehicles whose speed are between 63 miles per hour and 71 miles per hour will now become, because you already have their percent, you're going to be equals 68%. Okay, times how many vehicles that it has said? They said assume that the suppose the number of vehicles is 75%. So I'm going to put suppose the number of vehicles in the sample is 75. So I'm going to make n equals 75. Okay. N equals 75. Okay. So that means since we have the percentage already, just multiply it by 75. Which would be, of course, know that when you're multiplying percent, you gotta change it to decimal. So we've got 0.75 0.68 times 75. And that will give you the number of vehicles whose speeds are between 63 miles per hour and 75 miles per hour. So let's multiply this in the calculator. We got 0.68, 0.68 times 75. 51 vehicles, 51 vehicles of that speed. Okay. 51 vehicles. Vehicles have that speed. Now, another one is this. It says, in a sample of 25 additional vehicles, how many vehicles would you expect to have speed that exceeds 71 miles per hour? Now, n is 25. So I'm going to write n equal 25. Okay. N equals 25. Let me bring this down so we can have enough room. Okay. All right. Okay. This is our C. Good. So n is 25. N equal 25. So we can now estimate the number of vehicles. I'll estimate it right here. Make it 18. You can see I believe. So let's do it. Now, n is 25. So for speed that exceeds 71 miles per hour, so you go to the chart. This is 71 right here. 71 miles per hour is from here, see, from here up, which is 13.5%, plus 2.35%. You have to get the percentage. So you gotta give us the 13.5% plus 2.35%. So let's get the percentage before we multiply, okay? I mean, this is exceeding 71, so you cannot include 71, which means from here to the up. So we're gonna go about and put it equals so have it at the percentage as percentage would be 13.5% plus 2.35%, which give us from the calculator, we can get the answer from the calculator. We have 13.5% plus 2.35, 15.85%. 15.85. Let me write it down. 15.85%. So we're going to put it right there and then find the number of vehicles. So 15.85%. 15.85%. So this will give you the percent of vehicles whose speed. Then with that, you can now find the number of vehicles whose speed is 6.1 miles. And that becomes 15.85% times the n. N is 25. So we have, of course, you know that percent, you have to change this to decimal first before you multiply, which is 0. When you change the 15.85% to decimal, you're going to get 0.1585. And how do you change it to decimal anyway? Just divide it by 100 times 25. And that will give you the answer. The number of vehicles that have speed exceeding 71 miles. Let's go and multiply this in the calculator. So we have it here. We got 0.1585 times 25 vehicles. 3.96, which is 3.96, which is 4 vehicles. Okay. 3.96, which is 4 vehicles. Okay. 4 vehicles have speed exceeding 71 miles per hour. Now, any question on what I have done so far? Any question? Okay. So no questions then. Okay, good. Now, let us now that's an example of empirical rule. So solve as many examples as we can. Okay. Here, and let us look at another question that we use to that will reflect Chebyshev. Look at this question here. It says, that's number 15 question. It says, the average check at a local restaurant is $36.42 with a standard deviation of $8.15. What is the minimum percentage of check between $15.25 and $57.61? So this one didn't tell us whether it is symmetric or not. It didn't tell us whether it is normal. Unlike the other ones with this, if you look at the other question we solved, it says here, assume that the data set has a bell-shaped distribution, which now tells you that this is a good example for Chebyshev. The other one we solved also said the same thing, assume that the distribution is metric. So if the question doesn't say that, that means it is a good candidate for Chebyshev. Like this one, it doesn't say it. So I'm going to move it to next page so that we can have enough room to solve this. So this one didn't say anything. So now that means it's a Chebyshev. So the mean is $36.42. Write it out. And the standard deviation is $8.15. To find the minimum percentage, we need to estimate K first, which is K represents the number of standard deviations away from the mean. So to do that, we need the minimum percentage of check and the maximum percentage of check. I wrote them down here, lower and upper. So now let's find the K. To find K, we use this formula. Like here, the first one, the care, using the lower end, 15.25. The lower end is, to find care using the lower end, you do lower minus mean divided by standard deviation. Upper end is use upper minus mean divided by standard deviation. Let's find the lower end first. Lower is going to be, here will be, for the lower will be 15.25 minus mean of 36.42. Okay, divided by the standard deviation of 8.15. So let me add this here. I don't have nothing on this section anymore. No more rooms. So I got 15.25 minus 36.42 divided by 8.15. I'll give you the first K. So let's go and put this on the calculator. We have 15.25 minus 36.42 divided by 8.15. Negative 2.5975. Okay, negative 2.598, which is basically negative 2.6. Let me go and put it in there. Okay. Give us negative 2.598, which is negative 2.6. Approximately. Now, if you do the for upper end, you get the same thing. For example, let me do it. For upper, I'm going to use the upper amount, which is $36.42 minus the mean of so sorry, my mistake. The upper end is upper amount is $57.61. $57.51 61 cents minus mean of 36.42. Okay, divided by the standard deviation of 8.15. Okay, that gives us we got to go to the calculator again, and that will give us change this to, I think it's say 51. Let me look at it again. 50, okay, let me write down 57.61. So let's go and put that there. 57.61. Give me 2.6. I see that it is give the same thing. So we get 2.6. Now we have found that K is 2.6. With that, we can now find the percentage. But it says here, what is the minimum percentage of check between $15.25 and $57.61? The formula is this. So it said the minimum percentage of this check between $15.25 and $57.61. Since now we have K is found using this formula, 1 minus 1 over K squared times 100. So I'm gonna this place will not allow us to put this formula. So I will take you to where it will allow us to put it, the formula. I think I opened the, okay, let me say open this page for that. Well, let me open it. All right, okay, let me open it then. I opened it, this new workbook, so that we can go there and put the formula. So it says minimum percentage, okay? We're gonna insert the formula because the question says minimum percentage, okay, equals so So let me make this in big, make it 18. So now minimum percentile of the check. Okay, that will ask us between $15.25 and $57.61, knowing that the care is 2.6, is given by this formula: 1 minus 1 over care squared times 100, which is we have here equals, I'm gonna put this in parentheses, okay, and I'm gonna put so I got 1 minus 1 over care squared, okay, care squared, okay, times 100%. That's 100, which is in our own case, it's gonna be 1 minus 1 over and our care is 2.6 squared, okay, times 100 times 100. So which will give us the minimum percentage. I'm going to make it 14. If 14 be enough for it. Okay. Now let's go and put this in the calculator. I have, okay, 1 minus 1 over 2.6, okay, squared times 100, 85.2%. 85.2%. 85.2%. So the minimum percentage of the check, I'm going to copy this and put it on the main workbook. Okay. You're going to be the minimum percentage of the check between 15.25 and 57.61 is 85.2%. So the first person is to find your care. Once you get a care, you plug it into the formula to get the percentage that you are required. Any question on this? Yeah, no question. Good. Good. So let's do more example on Chebyshev. It says, let's see, Chebyshev. Okay, look at this one. It said that assume that the MBA students, assume that the average age of MBA students is 31.6 years old with a standard deviation of 2.8 years. So it says, I'll let the z-score. It says, this is just tear up. Oh my God. Okay, anyway, it says calculate the z-scores for the MBA student who is 28 years old. B, use empirical rule to determine the range of ages that will include 99.7% of the students around the mean. C, using Chebyshev theorem, determine the range of ages that will include at least 94% of the students around the mean. D, say using Chebyshev theorem, determine the range of ages that will include at least 80% of the students around the mean. So let's start from, first of all, let's always find the mean and the standard deviation. We are told that the mean average age of MBA students is 31.6 years. I have it here. Mean equals 31.6. Okay. And the standard deviation is 2.8 years. I have it here, 2.8 years. Now it says, A part says, calculate the z-score for MBA students who is 28 years old. So that means our X is 28 years old. So that our z-score will now become X, this is the formula right here. X minus mean divided by standard deviation. That means, in that case, our X is 28 minus mean of at 1.6 Okay, divided by the standard deviation of 2.8. So let us plot this into the calculator. I'm gonna write this down so we can plot it in a calculator. Okay. Okay. 28. Z equals 28 minus at 1.6 or 2.8. Okay. What is the calculator? Okay, right here. So you have 28. 28 minus 3, that's 1.6. Okay. Divided by 2.8 is negative 1.2. Okay. It's 1.2. That's what I got. This score. It's 1.29, matter of fact. But the question they ask us here actually is to find the let me see. It says calculate the z-score. Okay. So the z-score just put it in. So that will give us, because what we got from the calculator is let me put it right here. Negative 1.29. Let's call it negative 1.2. Negative 1.29 is the answer. So negative 1.29. So what does this mean? It means that the age of this student is 1.29 standard deviations below the mean. Now, this is using the empirical rule, determine the range of ages that we include 99.7%. Now, again, the mean is at 1.6 and the standard deviation is 2.8 years. Now, according to empirical rule, about 99% will fall within 3 standard deviations. So if I look at our empirical rule, what it says that about 99%, 99.7% will fall within 3 standard deviations. See, look at the chart. See, I mean, from here, add all this to this point. And you can even see it on my statement at the beginning, where I presented the Chebyshev, the empirical rule. It says that at least 99% of all values fall within 3 standard deviations. So with that in mind, can go back to that question. The question was asking us to it said that, let me see. Say using empirical rule, determine the range of ages that we include 99.7% of students. So, like I said, according to the like I said, and like I just showed you, according to the empirical rule, 99.7% fall within 3 standard deviation of the mean. So that means we're going to be using this lower range, mean minus 3 standard deviation of the mean, and upper one, 3 mean plus 3 times standard deviation. So we plug it in here. Mean is 31.6 minus 3 times standard deviation, which is 2.8. Yeah. So I'm gonna write this down. We got 31.6 minus 3 times 2.8. Let me go and put it on the calculator. We have we got 31.6 minus 3 times 2.8. Okay. I got 23.2. So repeat the same process for so let's go and put the answer first. Okay. 23.2. Now do the same thing for the upper range, except that now you put a plus sign. So that'll give us for the upper. Go to calculator and just change it to plus sign. Okay. 40. 40 years. So you have repeat this, except that you make it plus sign this time. Make it a plus sign. Okay, making sure you're seeing this, all of this. Okay. And it give us 40. Okay. Okay, so it gave us 40, which means that the range of ages that we include 99.7% of the students around the mean is 23.2 to 40 years. Okay. Now, last one is, second to last, using Chebyshev theorem, determine the range of age that we include 94% of the students around the mean. Now, according to Chebyshev says that 94%. It says that what is Chebyshev? Okay, say that at least 95% of the data value fall within 4 standard deviations. 4 standard deviations of the mean. So having seen that, we can now be able to answer the question. It says what percentage, or determine the percentage using Chebyshev to determine the range of ages that we include at least 94%. So this time around, Chebyshev said that it is 4 standard deviations. So that means our mean is still 31.6 and the standard deviation is 2.8. So in that case, for the lower end, we use mean minus 4 times standard deviation. And for the upper end, we use mean plus 4 times the standard deviation. So have mean is 31.6 minus 4 times 2.8. So I'm gonna do this 31.6 plus, sorry, 31.6 minus 4 times 2.8. Let's go and put this on the calculator. Okay. Just change this to 4. And change this one to minus. It was 20.4 years. So we can go and put this on our main workbook. We got 20.4 years. Yeah. So we do the same thing for the upper end. So that this time around we change this to a plus sign. Okay, change it to a plus sign. Let's see what it will give us. Let's see what it will give us if you try change it to plus sign, and we using the calculator. Okay, change it to plus sign right here. 42.8. That 42.8. Okay, 42.8 years. 42.8 years right here. 42.8 years. Which means that the range of age that we include at least 94% of the students around the mean is between 20.4 years to 42.8 years. The last one was asking us, using Chebyshev theorem, determine the range of ages that we include at least 80% of the students around the mean. Now, unfortunately, Chebyshev doesn't have any provisions for 80%. If you look at it, let me take you to the rule again. It says that this one is empirical. So Chebyshev say at least it has a rule for 89%, have a rule for 95%, and for 75%. But they don't have anything for 80%. So that means we have to estimate the care using an equation, okay, before we can apply it. So let's estimate it. To estimate the care, we're gonna use this equation for Chebyshev, from Chebyshev. That equation is right here. Again, remember that the mean is 31.6 and the standard deviation is this. But know that according to Chebyshev, the position of any data set lying within K, standard deviation is at least 1 minus 1 by K squared. So let's use this to estimate the K. So you have that. Make sure you're seeing this. Okay. All right, see. So we estimate the K. So you have it in this form. And I have that. Let me organize myself. So I have, it said, the question says anyway, using Chebyshev theorem to determine the range of edges that we include 80% of the student around the mean. So we're gonna use that equation. We have equals to have, I hope I can write this, but 1 minus 1 over, okay, I gotta clean this. Where's the eraser? Over K squared, K squared. Okay, times, okay, matter of fact, times 100%. I'm gonna use just equal. We already have the percent, so I'm gonna just put equals 80%. Okay. No, not this. I gotta erase that. Okay, equals 80%. Okay. So now, I'm going to push some of these things down so we can have enough room. Now, so that means that it means that 1, remove the parentheses, minus 1 over K squared equals, please pardon my handwriting, 0.8. 0.8, because 0.8 represents 80%. Okay. Now, of course, we can have the do the equation. Remember how you do your equation in algebra? You make this side stand by itself by removing 1 from both sides. So I'm going to remove 1 from both sides. Minus 1 and minus 1. And that gives me, the line is not good. I'm going to put a good line there. That gives me, let me make it a straight line. Okay. This one is gone. So I have negative 1. My handwriting in this, okay. Negative 1 over K squared. Negative 1 over K squared equal I have 0.8 minus 1. Okay. We got 0.8 minus 1. 0.8 minus 1 give us negative 0.2. Okay. Negative 0.2. Give us negative 0. Okay, I'm gonna erase that. Okay, negative 0.2. Okay. Now, we're gonna move down more to have enough room. So now, next thing is to make them positive by dividing both sides by negative 1. If you remember your algebra work, by negative 1 divided by negative 1. And that give us this is positive. So you have 1 over k squared equal 0.2. Okay. Now you flip it. Find the reciprocal of this. Okay. When you flip it, you're gonna have and find the reciprocal of both sides. Or that means reciprocal of k squared over k squared is k squared. K squared. That means the reciprocal of this means 1 over k squared over 1, which is k squared. And the reciprocal of 1 over 2 is, you flip it, 1 divided by 1 over 2. Okay? 1 divided by, sorry, the reciprocal of 0.2 is 1 divided by 0.2. So 1 divided by 0.2. Okay? And that will give us, my handwriting is, please pardon it. I'm trying to write with the computer. So now, that means that our k squared equals, now if divide this, let's go and divide it on the computer. Yeah. Come down here. Let's go and divide it on the computer. So you can have 1 over 0.2. So divide it on the calculator. 1 divided by 0.2. Have 1 divided by 0.2 is 5. So we're gonna put it 5. Okay. I'll give us 5. So k squared is 5. That means to find the k, I'm gonna write it from here. K squared equals 5. So find k, I'm gonna find the square root of that. Square root of k squared, and do the same. Anything you do on one side, you do on the other side. Square root. Okay. So let's find the square root of both sides. The square root of k squared is k. Okay. K. I'm gonna clean that and write it well. I'm gonna put k equals the square root of 5. Let's find the square root of 5 on the calculator. The square root of 5, clear this, square root of 5, 2.2, 2.2, approximately, 2.2. So you got k is 2.2. So we have found our k. We can use it to answer the equation, because the equation was using Chebyshev theorem to determine the range of ages that will include at least 80% of the students. So all this thing we are solving, because the Chebyshev doesn't have a prediction for 80%. So that means we have to estimate our k using that formula, this formula, which is what we did in this equation. We find our k to be 5. Now we can to be 2.2. Now we can now get our lower range. So mean, remember that the mean is still at 1.6, and the standard deviation is 2.8. So let's use to find the lower end. At 1.6, you get at 1.6, lower end at 1.6 minus 2.2 for k times the standard deviation of 2.8. That will give us the lower end. Okay, we'll write this down. at 1.6 minus 2.2 times 2.8. Okay. We got that 1.6 minus 2.2 times 2.8 is 25.44. So I'm gonna put it right there. 25.44. Got 25.44. Then repeat the process for the upper end, so that this time around you use plus sign. So I'm gonna go there and calculate and put plus sign. Okay. That's 7.76. That's 7.76. Okay. So we're gonna put the same thing about plus sign this time around. Okay. So we got that's 7.76. So which means that the edges that we include 80% is between 25.4 and 37.8. Now, any question on this? Any question before we leave? Here.
No.
So then I'll see you guys next week. Have a nice weekend.
Have a good one.
You